Hey there, science fans. Today we're diving into the exciting world of calculus. We're going to explore two fundamental concepts, limits and continuity. Now, don't let those words scare you. They might sound complicated, but trust me, they're not as scary as they seem. In fact, they're actually pretty cool. Imagine you're trying to figure out how fast something is moving at a specific moment. Or maybe you're trying to determine the exact area of an irregular shape. That's where limits and continuity come in handy. They are the mathematical tools that allow us to analyze change and motion with incredible precision. Get ready for a wild ride as we unlock the secrets of these powerful concepts. Think of limits as a way to sneak up on a specific value. Imagine you're walking towards a wall. You can get closer and closer to it, but you can never actually touch it, right? Limits work in a similar way. They allow us to see what happens to a function as we get closer and closer to a certain input value, even if we can't actually reach that value. Continuity, on the other hand, is all about smoothness. A continuous function is like a smooth, unbroken line on a graph. There are no sudden jumps, holes, or gaps. Understanding continuity helps us determine if a function behaves predictably and allows us to make accurate predictions about its behavior. Let's start by defining what we mean by a limit. In the simplest terms, a limit describes the behavior of a function as its input approaches a certain value. Think of it like approaching the edge of a cliff, but not actually jumping off. We're interested in seeing what's happening as we get closer and closer to the edge without actually going over. Mathematically, we write the limit of a function, f(x), as x approaches a certain value. Let's say a, like this, lim xa, fx equals sine L. This means that as x gets closer and closer to a, the value of the functions fx gets closer and closer to L. Notice that x might never actually reach a, and that's okay. We're interested in the behavior of the function as it approaches a. Now, there are two ways to approach a value on a number line, from the left and from the right. We can define left-hand limits and right-hand limits to describe the behavior of a function as x approaches a from either direction. If both the left-hand limit and the right-hand limit exist and are equal, then we say that the limit exists and is equal to that common value. We can also talk about limits at infinity. This might sound strange, but it simply means we're interested in the behavior of a function as x gets infinitely large or infinitely small. Just like driving a car, there are rules that govern how limits work. These rules, called limit laws, help us calculate limits more easily. Let's go over some of the most important ones. 1. The sum and difference rule. The limit of a sum or difference of two functions is equal to the sum or difference of their individual limits. 2. The constant multiple rule. The limit of a constant times a function is equal to the constant times the limit of the function. 3. The product rule. The limit of the product of two functions is equal to the product of their individual limits. 4. The quotient rule. The limit of the quotient of two functions is equal to the quotient of their individual limits, provided the limit of the denominator is not 0. These rules provide a framework for working with limits. They allow us to break down complex functions into smaller, more manageable pieces, making it easier to evaluate their limits. Another important property of limits is uniqueness. This means that if a limit exists, it can only have one value. In other words, a function cannot approach two different values at the same time. This property is crucial for ensuring that our calculations are consistent and reliable. Sometimes when we try to evaluate a limit, we run into situations where the limit laws don't give us a clear answer. These are called indeterminate forms. One common example is when both the numerator and denominator of a function approach 0 as x approaches a certain value. This is where a handy tool called L'Hopital's rule comes in. This rule states that if we have an indeterminate form of the type 0 over 0 or infinity over infinity, we can find the limit by taking the derivative of both the numerator and the denominator and then evaluating the limit again. L'Hopital's rule can be a lifesaver when dealing with tricky limits. It allows us to bypass the indeterminate form and find the limit using differentiation. However, it's important to remember that L'Hopital's rule only works if the original limit is in an indeterminate form. Section 5, special limits, shortcuts and familiar faces. In calculus, there are certain limits that pop up again and again. These are called special limits, and they're like shortcuts that can save us a lot of time and effort. Some common special limits include, first, the limit of a constant. The limit of a constant function is simply the constant itself. This is because no matter what value x approaches, the function always stays the same. Second, the limit of x. The limit of fx equals x as x approaches a is simply a. This is because as x gets closer to a, the function value also gets closer to a. Third, the limit of sin x over x. This is a classic limit that appears frequently in trigonometry and calculus. As x approaches 0, the value of this limit is 1. These special limits are like familiar faces that we can recognize and work with easily. By memorizing these limits, we can quickly solve a wide range of problems without having to go through lengthy calculations each time. Section 6, continuity, a smooth ride. Now that we have a good understanding of limits, let's move on to continuity. In simple terms, a function is continuous if we can draw its graph without lifting our pen from the paper. This means there are no sudden jumps, holes, or gaps in the graph. Mathematically, a function f(x) is continuous at a point x equals a if three conditions are met. First, fa is defined. The function has a defined value at x equals a. Second, the limit of the function as x approaches a exists. Third, the limit of the function as x approaches a is equal to the function value at x equals a. If any of these conditions are not met, then the function is said to be discontinuous at that point. There are different types of discontinuities, such as removable discontinuities, where the function has a hole at a point but can be made continuous by redefining the function at that point. Jump discontinuities, where the function jumps from one value to another. And infinite discontinuities, where the function approaches positive or negative infinity. Section 7. The intermediate value theorem, connecting the dots. The intermediate value theorem, or IVT, is a powerful theorem that relates to continuity. It states that if a function is continuous on a closed interval, ab, and if c is any number between fa and fb, then there must exist at least one number x in the interval, ab, such that fx equals c. In simple terms, the IVT guarantees that if a function is continuous on an interval and it takes on two different values on that interval, then it must also take on every value in between those two values. For example, let's say we have a function fx that is continuous on the interval 1, 5. If we know that f1 equals 2 and 5 equals 10, then the IVT tells us that there must be at least one value of x between 1 and 5 where fx equals 7. The IVT is a fundamental theorem in calculus and is used in many different areas of mathematics, including proving the existence of solutions to equations and approximating solutions numerically. Section 8. Limits at infinity, journeying to the horizon. We've talked about limits as x approaches a finite value, but what happens when x gets really, really large, approaching infinity? That's where the concept of limits at infinity comes in. A limit at infinity describes the behavior of a function as x approaches positive or negative infinity. We write the limit of fx as x approaches infinity as limit as x approaches infinity of fx equals L. This means that as x gets larger and larger, the value of fx gets closer and closer to L. Limits at infinity are closely related to the concept of horizontal asymptotes. A horizontal asymptote is a horizontal line that the graph of a function approaches as x approaches infinity. If the limit of a function as x approaches infinity exists and is equal to a finite value L, then the line y equals L is a horizontal asymptote for the graph of the function. Section 9. Real-world applications, limits in action. Limits and continuity are not just abstract mathematical concepts. They have numerous real-world applications in various fields, including physics, engineering, economics, and computer science. In physics, limits are used to define instantaneous velocity and acceleration. Imagine a car accelerating from rest. We can use limits to determine the car's velocity at any given instant in time, even though the car's velocity is constantly changing. In engineering, limits are used to design structures that can withstand stress and strain. For example, engineers use limits to calculate the maximum load a bridge can support before it collapses. In economics, limits are used to model and analyze market behavior. For instance, economists use limits to determine the equilibrium price and quantity of a good or service. Limits and continuity are essential tools for understanding and analyzing change and motion in various real-world contexts. They provide a powerful framework for making predictions, designing solutions, and advancing our understanding of the world around us. Section 10. Conclusion: Building blocks of calculus. Congratulations! You've just completed a whirlwind tour of limits and continuity, two fundamental concepts in calculus. We've covered a lot of ground, from defining limits and exploring their properties to understanding continuity and its implications. Remember, limits are all about approaching a value without actually reaching it, while continuity is about smoothness and the absence of abrupt changes. We've seen how these concepts are essential for understanding derivatives, which describe instantaneous rates of change, and integrals, which allow us to calculate areas and volumes of irregular shapes. From physics to engineering to economics, limits and continuity play a vital role in solving real-world problems and advancing our understanding of the universe. So keep exploring, keep questioning, and keep pushing the boundaries of your knowledge, because with calculus as your guide, the possibilities are truly limitless.